Hey everybody, and welcome to our webinar today. My name is Paul Bemis. We're going to be discussing raised versus non-raised data floor center designs. If you don't know us, I think most of you do. This company that I own is Applied Math Modeling. It is a spin out of the Ansys Corporation. I worked there for many years, both on the structural mechanics side and also the fluid dynamics side. CoolSim is built on top of this technology. We use the Fluent set of mesh solved post engines or solvers or technologies on a cluster. That's a SaaS model, and CoolSim is extremely good. It's getting really quite robust in terms of its ability to do most anything. We are experts in the field of CFD, and we have, of course, full Fluent at our disposal. So if for some reason you need something done that isn't typical in a data center, we can model it for you as a consulting project. So let's talk about modeling. A lot of the discussion today is going to be about modeling, about CFD modeling. We have the opportunity here at Applied Math to see an awful lot of designs, and I'm going to effectively teach you what I've learned over the years, over the many years. In general, an air handler is a term, AHU, air handler, to define the cool air that enters the room. It can come from a variety of sources. It could come from a DX unit. DX stands for direct expansion, so the compressor may be inside the unit and it's blowing air from the compressor, and it has a corresponding condenser that sits outside. Could be a fan coil, which is common in chilled water, where you've just got a fan and a coil, and the liquid going through the coil is coming from a chiller or other source. It can also be delivered by duct. It can be the outside air. In mining currency applications, they're often using free air. So they're just pulling air in, often through an evaporative media, into the data center. It doesn't really matter to us, because what we're concerned about in this analysis is the delivery of air inside the room. So what matters most to us is the size of the outlet. That is, how big is the size of the device that's delivering air, whether it's a duct or an outlet, because of course that determines the velocity. So remember that cross-sectional area and mass flow will derive velocity. So the area times the velocity equals the mass airflow rate, and therefore the size is important. The smaller the outlet, the higher the velocity. Those are direct trade-offs, and so you want that velocity, as you'll see, to be as low as you can possibly get it. Having said that, the mass flow rate on these things is high. As we get to bigger data centers and more intensity, more wattage, we have larger mass flow rates. They are proportional. And so the mass flow rate determines the amount of air that must enter the data center to cool it. The other important parameter here is simply supply air temp. So these are the most important. The size, the geometry, by the way, placement is important. Where those ducts are or where that supply is in the data center, you'll see is important. Its mass flow rate and its supply air temperature. These three components alone are sufficient. Now, many will say, well, what about cooling capacity? Well, cooling capacity is not that much of an issue in data centers because, generally speaking, you have enough. It's fairly easy for someone to calculate how much cooling capacity they need by simply doing straight arithmetic. If it's a megawatt data center, you need a megawatt of cooling capacity, or plus n, so plus 1, so you need a little more. It's fairly easy to do that math, and so data centers generally have enough cooling capacity in their base design. The issue is getting the air to the right location to cool the servers. The governing equations for this, same one I reviewed last time when we talked about containment. This now I'm talking about air handlers. The heat transfer Q is equal to the mass flow rate times the density times the specific heat of air times delta T. So it's the delta T that you're looking for. That's on the server side. That's what's generating the heat. The density will change a little depending upon temperature, right? Ideal gas law. And what's happening is as temperature rises, so won't pressure, and therefore density will change. We'll see this in practice as we begin to look at these models. The other one I want to bring to your attention is pressure. This is something that, again, falls out of the Bernoulli equation for low-speed flows. Generally, we model these as incompressible because the pressures we're talking about here are very, very small in a data center. This is not a high-pressure situation, and it's not an aircraft engine or an internal combustion engine. We don't really have to worry about compressibility of the air. With that in mind, total pressure equals static pressure plus dynamic pressure. What I mean by this is that these trade off for one another. If you have velocity in the air, so you have fast-moving air, your static pressure is going to drop. The relationship of these two components right here, as they trade off against one another, are very important in data center design because it is static pressure that allows air to get to where it needs to go. In particular, when you're talking about containment, you want to try to maintain a pressure differential between what is in the room and what is in the contained area. And that pressure differential is important for maintaining a robust design. When you introduce velocity, that changes the pressure differential, and we'll see the effect of that in the CFD models. So again, a total pressure is static pressure plus dynamic pressure, and we're going to watch these things trade off. So to get started, I'm going to do a submodel here, and I'm not going to use a lot of slides today. I'm going to use CoolSim. So the first thing I want to show you here is this fairly simple design. This is a slice of a common data center that I see. I'm just going to point out the pieces of it here, and then we're going to go to the modeler and begin to look at it. So here what I have is a non-raised floor design. This is sitting on a slab. So there's no raised floor here. Air is coming down from above. The ceiling is indicated here in this green line. So we make the ceiling transparent so you can see through it and see what's going on in the room, but it is there, and it is assumed to be non-leaking. It does not leak. It's perfect. This is not true in real world. They do leak, and I'll show you the effect of leakage a little later in our program today if I have time, because we did model one with leakage in the ceiling, and it isn't pretty. These devices right along the top here, this piece are ceiling grills. Those are sitting in the ceiling. This gray is containment. So this is a hot aisle design, hot aisle contained design. The air will come down through these devices. Now I've got these modeled right here as just devices that we call these generally CRACs or air handlers. The term in CoolSim is a CRAC. But again, all I'm really interested in is the air entering. These are typically overhead units. They're up on the roof, dumping air down. They could be enthalpy wheels, like a Kyoto, what was called a Kyoto unit. They're trying to do the best job they can, delivering cool air at lowest possible cost. Generally speaking, if you're trying to absorb outside air, the devices tend to be big because you need a lot of surface area, so these units tend to be big. And so they sit outside the data center, usually on top of the roof or some other place. They dump air into the room via some ducts, and there's usually a supply plenum along this line here that comes in. This device along the wall is generally a screen of some kind with a percent area open on it. And the reason that that is done is to try to unify the flow across this section in the case one of these units is off. So in the N+1 case, when you're only using a certain number of these units, you'll get a very different airflow pattern. And that's an important case to study because it will dramatically affect the cooling in the room. So the way this room works, again, is you have two air handlers here dumping air down into the room, coming down, turning this corner, and flooding this room with cold air. They often call this a flooded room design. And the simple thought is, if we flood the room with cold air, there's enough volume there, so everything should be good. And we contain the hot side, as you can see here, and all the hot air goes back up into the ceiling plenum. Everything's good, right? We don't need to run CFD on this. This is what I often hear. We don't need to model this. Everything's perfect. Not so much. So I'm going to show you that design, and then I'm going to pop open. Oh, let me do one last thing before I go. The parameters on this from the pre-simulation report is shown here. So pre-simulation report in CoolSim just allows you to make sure that your numbers are correct. The most important are these two right here. The supply air from those downflow units need to be sufficient to meet the demand of the rack. Remember, the rack needs about and I'm afraid for my international friends, I'm going to use American units here because that's the most natural, I suppose, to me. And so I'm going to use CFM. But the fact is that the supply must exceed the demand by a certain amount. In a perfect world, from an energy point of view, I would run these equivalent to one another. That the best design would be 90742.6 for supply, because that's exactly what the racks need. Getting these numbers closer to one another optimizes the energy efficiency, because you can run your fans lower up here on the supply side, and your heat transfer will be better. The slower the air across the coil, the better efficiency it has, because it picks up more heat or more cooling, depending which way you're going. And so you want that to be as close to one another as you can. That's called an RTI for those of you who have been to the Department of Energy training. That's RTI, the room thermal index. You want these to be close to one another. Okay, so that's a key point. All right, so I'm going to go get this data center over here and drag it over into the scene. There's a little multimedia work going on here. I hope I'm sharing. Somebody please tell me if you cannot see this. Please send me a note. Last time I forgot to share, so I do make mistakes. All right, so a couple things about this. I'm going to first show you how I built it, because for those of you who are CoolSim users, there's a number of you in the audience, this is a really good way to model leakage. So in this environment, I have the walls of the containment are set as baffles. I'm using baffles everywhere. I do that intentionally because a baffle is a very low-cost CFD element. So it is a zero thickness partition on the mesh. A little bit probably more information than you need to know, but in this case, it's just really easy to use them. They're inexpensive from a computational point of view, and they allow leakage. So that's a nice thing about it. And here I'm building the walls. I have them in room, which means it goes right from the floor to the ceiling automatically without me having to worry about it. And they are full size of this entire area, including the racks. Now I've got this set at 0, no flow. So I've got that box checked off, meaning it will not allow flow through it. So the question becomes, how does my rack dump air into that hot aisle? And you will see what I've got here, and I colored it so you could see it. On the back side, I have another baffle. In CoolSim, it works on the order of preference in terms of what was played into the data center in terms of time. If this baffle were placed after the first one and they're coplanar, the parameters of this one supersede the one that it's on. These are coplanar. They're on the same plane. I'll show you that in a moment. And here I've got the airflow set to 95%. This means it's open behind this device. So again, let me just show you how this is done, because it's a very effective way to model. And you see here that this plane right here is coplanar to this one. They are the same, in the same direction in X, exactly coplanar. But because I placed this one after this one, the orange one, has precedence of parameter. And this is a fluent construct. I didn't do it this way. It's the way the program works. But because it was placed there last, its parameters succeed. So that means I've cut a hole in that, which implies that I don't have to worry about this being any other than a solid block or a solid entity. I don't need to worry about cutting a hole in it. This other baffle right here will act as the opening, okay? So that means the back of my rack, and my rack is here just a normal rack. You know, it's nothing special about it, except in this case, I have a baffle along the side of it as well. And that's grouped right there, so I can ungroup it. CoolSim supports grouping. So I just laid these in. I really just made one of them. You can see that's why it was grouped. I made one of them and then cloned it. Cloning is a very effective tool. In CoolSim, it allows you to replicate with offset. So to build this, all I did is set up one of these. You can see it right there. I got that structure right where I wanted it. The gapping I have between these is about 3 inches on either side. Be careful, because if you go too tight, your mesh count will go way up. 3 inches is fine, 3 or 4. That's normal anyway. And what's represented in green here are the rack rails. This is where data centers leak. They leak in the rails. This is a rack rail. I have rack rail leakage. I can set that parameter. That parameter for this design is 10%. I'm assuming 10% leakage, which I think is probably gracious. They probably leak worse than that, but that's how I have it set at the moment. And you also see there's a gap underneath these racks. So this is a fairly accurate representation of the real world, at least as much as we know. There is no real data on leakage because everything's very different. It's very hard to get good data on how these things leak. It depends upon many factors, including how the data center was designed, who put it together, literally, who put the racks in, did they seal properly, did they manage their cables on the backside properly. But this is the best representation that I have seen. It's not expensive computationally. So here you see the rack rail. The sides are also made out of baffles. Everything here is made out of baffles. The sides are set for no leakage. The rail is set for 10%. The back is open, about 90%. And then the containment is solid. The containment usually doesn't leak on these surfaces, this one and that one. And then I have grills at the top. Okay, so I wanted to just show you how I built that. Again, once you build one of these structures, so here in top view, once I have one of them, I can take this entire structure as an assembly, and I can group it, and then I can clone it. Cloning allows me to replicate it with offset. So laying out a data center is very fast once you get the first structure done. There's a lot of symmetry in the data center. So you can take this one entity now and just clone it n times in any direction and lay out your entire data center. But for the purposes of this discussion, I wanted to just look at two racks and show you what's going on here. So now I'm going to go to the output. This model has been run, and this is what the output in CoolSim looks like. I can also share this with you if you're interested in looking at this output yourself. I can share this with you. Let me see if I can do that. So CoolSim now supports hyperlinks. So I can hyperlink you to the same exact structure. Let me make sure it's the same one. This is what I'm doing on my other screen. I've got a URL here. CoolSim now also provides the ability to share output with you without you having to load any special software. I'm just making sure it's the right one. So in your chat box, I am going to paste the URL for this this output, just to both show you. Control V. So in your chat box at the moment, there's a URL, and that URL is this output report. Now I'm going to go through it here, but I placed it there so that you could manipulate it as well. You could have a look at it. That link is live. Every time I do a simulation, we get one of those. I get one of those, and if you're a user, you will too, if you request it with CoolSim 5, and so you can share. Okay. So let me take a look here, first of all, at the data center energy report. Now, we're not doing energy in this case, but I want to see the RTI. RTI is, again, the return temperature index, or sometimes what I call the room thermal index, either one. And it's 96. Now, this is a ratio of the rack demand divided by the amount of air coming out of the air handlers. You noticed earlier, I pointed out that I'm delivering 96,000 on demand of 92. I should have plenty of air. There should be no issue with this data center. If I could get this air distributed evenly, everything would be great because I've got more than enough. And also, I'm showing no issues here with temperature. So RTI high is 100%. All three of these are optimization parameters. All three should be 100. And if you look, my rack numbers here look pretty good right now. So over here is the 3D files. The most important one is, of course, the recommended temperature. This is a compliance plot that we use. And you see here, everything's okay, that we're green. This is, for those in America here, this is the Kermit the Frog, life is green, everything wants to be green. Green means that I am above the minimum. I did this in SI, I guess. And the 27 is the max, the height, okay? Got the upper limit on color. I'm sorry, upper limit on temperature. So what happens here is if there's any red, and you see it starting to show a little bit of red over here, okay? So why are we showing a little bit of red? So let's take a look now at some of the other flow characteristics going on in this room. Let's take a look at Pathlines. This is always a good one just to get a feel, and this is from CRACs. We get a feel for what's going on in the Pathlines. Are they both running? Yes, they are. They're both running. Okay. So now the air is coming down and bouncing off the bottom like that, and then going up. You can see some dynamics in that room. You see it bouncing and then flowing up, upwards and down the line. Okay. And what we're concerned about in particular is velocities. How fast are they moving? Now, the velocities can be seen from velocity plots. I have a number of them here. So let's take a look at y equals 6. So it's 6 feet. Yeah, this is in feet per minute. Let's take a look at some velocities and see what's going on. So I use keystrokes here. CoolSim supports keystrokes on this. This is all Ansys technology. So I'm going to do a Y. And I'm going to use the letter N, which turns off perspective and gives me a nice shot right there of what's going on. Notice what's happening. As this air comes rushing down, it starts to get into this area, and it's a little narrow here, right? So the air is bouncing down. This is velocity, and it doesn't give me the vector. It's just straight velocity. I can't see which way it's going, but I can see that on the edge of this leading edge rack, there's some very high velocity there. And that will cause dynamics. You will notice at the other end, there is no velocity. So it declines as it goes across, and that's normal. Well, take a look at what happens in temperature. So I'm going to do a temperature slice at y equals 6 feet here. I've got leakage turned on. And let's take a look at this dynamic. Again, I'm going to turn this thing around. I'm going to turn off perspective so we get a nice clean cut. And you see some leakage here, right? So what's happening, we're looking straight down at a height of 6 feet into that room. And you see what's happening here is these rails are leaking. There's the rack rail right there. It's in a black line. And you see some high temperature pressure starting to push. You see that temperature starting to push through those rails and leak into the cold aisle. And even though I'm still in compliance, this could be an issue and will be an issue as I tend to increase the load in the room of, right now I'm operating with the racks at 8 kW. So each one of these racks is 8, which isn't a big number right now. These numbers are getting larger and larger. So 8 is not that big. And we're seeing some back pressure here that's causing the temperature to push, or the air to push through and leak into the inlets. And you notice it's more pronounced on this end. You see it leaking here and leaking here. This one in particular, the air is coming by, causing low pressure, causing leakage right along these rails. As we get to the other end, things look a little better, right? Down here I have less velocity. So as the velocity declines down this aisle, the pressure differential gets better between these two, and I'm able to hold that in pretty well without any leakage. You can look at this a number of different ways. We're looking at this right now as temperature. You can also view it using pressure and see the same effect. Pressure is a little tougher to see it because getting the pressure range correct is a little bit challenging. One of the reasons this is true, and I think I pointed this out last time, is that in the hot aisle, and I'm going to show you pathlines from RACs and PDUs. In the hot aisle here, and I'm going to bring this around and show you the dynamic. So I'm going to use the Z key, turn off the perspective, and then in the upper left-hand corner of these little viewers that Ansys is providing to us, thank you very much, is a couple of ways to turn off some of this detail so that we can have a cleaner look at what's going on. I tend to just switch them until I get a clean look. There's what I wanted to show you. So in the hot aisle, we have this, again, dynamic going on where the air is coming out of these servers at a fairly high velocity on both sides and banging into each other right in the center. The first equation I talked to you about is static pressure, or total pressure being the sum of static pressure plus dynamic pressure. So with the change in velocity here, so as these two servers have air coming out, hot air coming out that's hitting one another, their direction is changing. And as their velocity slows down, the static pressure goes up, right? Because the static pressure plus the dynamic pressure is the total pressure. And that causes pressure in that hot aisle compared to the cold aisle in certain parts of that data center. So you say, well, I want the pressure in the room to be higher than what's in the contained area. That's generally what you try to do. You flood the room with cold air. But on the hot aisle, you've got inconsistencies with respect to pressure. And oftentimes that hot aisle will be a higher pressure than the outside air around it in the room, even though you're supplying more air to the room than is being demanded by the racks. That you would think that if I'm supplying more than I need, the pressure in the room would be constant. It would be higher than that in the contained area. That is not always true because of this effect. If these racks are too close together, this will cause a high pressure region. So these designs tend to be, the white space is expensive. So I want to put as much of this IT equipment as possible in there. And trying to stack it too closely together will cause some issues that aren't necessarily obvious to the casual observer. And this is one of them, that on the hot side, as these racks displace their hot air towards the center, there will be a pressure gradient that will sometimes pop in there, and it's nonlinear. In fact, it changes as a function of distance. So let's take a look at a pressure slice at 7 feet, and you'll see that variation. So what I tried to do here, again, I'll flip this around. This is a pressure gradient. We're looking at pressure now, and I probably don't have the range perfect yet. I'm probably a little too tight down here. But I wanted to show you that, for one thing, it's not uniform. And for another, the pressure differential between the hot aisle, which is here, and the cold aisle, which is over here, is not pronounced. It's not too bad over here. You see, I've got a pressure differential on this side, but due to the velocity in this narrow aisle, I have not much differential here at all, and certainly none down here. And that's what's causing the leakage to occur. The pressure in the room in certain locations of those rack inlets is not higher than what is in the hot aisle. The hot aisle is winning and pushing it back through. That's a result of high velocity coming in. Now, there's not much you can do about high velocity coming in on a non-raised floor data center. You can try to break it down. In fact, in this design, they're coming straight down and bouncing off the floor, which tends to reduce the amount of velocity because it bounces and slows down, and that's naturally a good thing. I'll show you a design a little later on where these are 90 degrees. It's a fan wall and it's blowing down the aisle. And as the velocities get high on these aisles, leakage starts to occur. And leakage is the nemesis of these designs. Containment is a good thing. That allows us to get the densities up. but leakage in those contained areas can be problematic. And the problem in this kind of design is there's no way to modulate that. The issue here with respect to non-raised floor designs like this is there's no way for me to modulate the amount of air getting to these racks compared to the air getting to these racks. It's all just flooding the room. So if these leak, if this situation up here is leaking for some reason, then all the air is going to escape into the ceiling plenum. There'll be no cool air further downstream. And they always leak. The question becomes, how much did they leak? The other important parameter here is that if you are not responsible for the implementation of the servers into these cabinets or the placement of these cabinets in these rooms, like is true for many co-location suppliers, then it becomes extremely difficult for you to manage that leakage because it's not in your control. It's somebody else's control. So to a large extent, these, I believe, have been promoted as a lower cost option because you don't have to pay for the raised floor. And because they're, quote, contained, they should, quote, work fine because there are no issues. It's fully contained. You don't need to run CFD on them. This is what I've been told by some. But the more we see them, the more issues we find with them. So now let me take that same design and I'm going to switch over now and I'm going to take a look at the same model with raised floor. Now all I did here was take the same exact design and put a floor plenum underneath it. Now my floor plenum is 4 feet. It's a fairly deep plenum. The deeper the better because again you reduce the horizontal flow velocity. You've got the same issue here as you had before with respect to getting the air down the line. The difference is that you've got a control parameter here called a dial row. And you can adjust the amount of percent area open so that you can modulate the air coming down that aisle in case you have trouble. You can do things like take tiles out if the rack is not in place. The other design we could not. We could not reduce the flow to sections of the room that did not need it. Here you can. So modulating the air being supplied to the servers is easier with a raised floor data center. Operationally, this is easier. Now, also in terms of performance, let's just take a look at some of the same plots. For one thing, this one is going to show up and probably, well, first of all, let me just make sure that show you that the parameters are all the same. So here where we saw a little bit of bleeding, a little bit of red in some of these sections over here, now no longer the case. This is now in pretty good shape in terms of temperature. If we look at the full range of temperature, you'll see it's in good shape as well. Pretty even throughout the data center. A little bit of a variation of temperature here. So in this section of the data center, we're having a little bit of trouble further down. It's not a problem up here now, it's a problem down here, and that's because, of course, the air is being dumped out and there's less down here. And it's quite likely we've got some underfloor velocities there as well that are causing some of that. But now let's take a look at the pressure. Let's first look at the pressure. Let's go to pressure at 5 feet, same slice we had before. And you can see here that this is a slice at 5 feet. Now what you want again is your pressure to be highest outside and lowest inside. You see I've got a nice pressure differential here. That looks good. I want blue to yellow. That's a good pressure differential. Here I'm down at this end, I'm beginning to lose it. I'm beginning to lose my pressure differential and you see some starting to leak back through. So it's just the opposite in a sense of the one you had before. So where the other one was bad up here and not so bad down here, this one, it's just the opposite. And this is quite typical of a raised floor design. Here we're having a little bit of high pressure. We're 0.005 compared to this range point, right around 0 actually, 0.0. And by the way, this is inches of water, but it doesn't really matter. Some people get very concerned about the units. Remember, in the case of pressure, what you are most interested in is the differential pressure. So the units don't matter that much. You're just interested in the differential. So now let's take a look at temperature. We'll take a look at temperature at a slice here. We'll go Y 6 feet. And you'll see a similar behavior, but it's just a little easier to manage it now. So let's take a look. Again, top view. You see they're much better than they were. Certainly down here, where it was leaking through that rack rail earlier, it's not anymore. I have plenty there, and as we move to the back and we see that pressure differential, it starts squirting out again. So down here on this design, I had a little bit of problem in this range, but still good over here, and this one could be managed. It's manageable. You could increase the amount of air, cold air coming out of the tiles. In other words, you can bias it. You can start to say, well, I'll run 25% open down here, then down here I'll open them up. You have, from an operational point of view, the opportunity to have more effect over hot servers or hot sections of the room than you did in the other case. So that is what I wanted to show you here on these two designs. The tiles were all uniform here. I did not vary them very much, and we can take a look at their performance as well. There's a nice plot over here on the left that comes with CoolSim that allows you to look at those tiles, the amount of air coming out of each one of them. It's called flow rate on tiles. We put this in particular so that you can manage the flow rate. And let me just show you that one. It takes a moment for that one to open. So here is the flow rate on tiles. Going to do Y. Going to, I'm just turning on my questions here to see if any of you are asking questions. Feel free to ask questions at any time. If you want to speak, put your hand up and I'll try to open your microphone. Here I'm going to turn off blocks. I'm going to turn off the raised floor in the rear. There we go. That's a nice shot. So here is the performance of these tiles as a function of position. This is quite normal for a raised floor data center. All the air in the plenum is moving down here, so I have high velocity air under the floor in this section, causing these tiles to underperform. And then down here, I have high pressure, so these tiles will flow a lot harder. You see, this one's not really doing much at all. It's near zero. And these are quite high. We've got a factor here of an order of magnitude in performance of these tiles based on position in the room. Again, as the velocity of the air under the floor comes down and hits that wall, the static pressure rises and the air comes out of the tiles. Now, generally in these kinds of designs, because we have high velocity in this direction, these don't perform well either. So if you look at Pathlines, for example, you can often see them bending due to, again, Bernoulli, that as the air travels under the floor, let's see if we can see them at all here. I don't know how many Pathlines I have turned on. But as the air comes underneath that floor and races down the plenum, the supply plenum, not too bad. You can see here the air coming down. This is in feet per minute. So as it passes this section right here, we're still operating at a range of about 400 to 500 feet per minute. That's pretty fast. And you can see those Pathlines bending. So they have momentum. They don't want to go straight up. You can see them bend right there. And that's a result of the Bernoulli again. As it comes down, high velocity, you want it to come through there. It doesn't have the pressure. And when it does come through, it comes through at an angle. And you can see it in the surfaces of the racks themselves. If you go up and you take a look at the full range of temperature, you will see that the leading edge of those racks is going to bleed a little bit. Not showing it much here. The temperature is 70. This is behaving pretty well. So you can't really see the effect on that edge, but it's there. It's just not bothering us at this point because we have enough air. We are seeing a little bit of a problem here. As I mentioned, these are leaking a little bit due to the velocity and the lack of air by the time you get there. But because you have tiles, you can begin to bias this design to make up for that. Basically, steal from Peter to give to Paul is a saying that we use a lot, right? And I've only got one tile in front of each one of those. And these are 8 kilowatts per rack, so they're going to need at least 800 feet per minute of air to make them happy. Okay, so no, 800 cubic feet per minute, not feet per minute of air. So the rule of thumb to keep in mind is that for each kilowatt of power, you need about 100, for new servers, you need about 100 cubic feet per minute of capacity of air to satisfy it. That's new servers. Older servers want a little more than that, so you can use a number of 125. Sorry, my international friends, I'm using US numbers. So from a airflow management point of view, there's no question that raised floor designs are easier to deal with. They're easier to manage the supply into the data center. So those are two designs. I wanted to show you the submodel there. Now I'm going to go to something a little bit bigger. So there's my submodel, second one. I've already done that. Here's the next one. And I wanted to show you this one because this is a bigger data center. I wanted to show you some of the leakage issues that occur when you do this. You notice same kind of design, air is coming down. I used this same model once before. So air is coming down through the walls here and into the room. And in particular here, I wanted to show you what happens in this kind of design under certain scenarios. So I'm going to bring over this model, and we're assuming here, and I have one of my friends in the audience today from Armstrong. I've been working with them a little bit on ceiling leakage. And we are assuming our ceilings are perfect here, which is not true. The ceiling does leak. Most of them leak. I've been in data centers where the ceiling is nothing more than a drop ceiling, that the same kind I have in the basement of my home. Those are notorious for leakage. And if we're going to assume that all the air is coming back to this air handler, and there's a pressure gradient across the ceiling caused by these air handlers pulling, then I need a ceiling that is uniform. In this design, I put some leakage along the far edge. You can see it right here. This is just simply a tile, or ceiling grill, that is. And I made it a certain width, and I opened it up at 80%, but the size of it is quite small. So we could use that as a percentage. In the room, it's not uniformly distributed, but it is a way for me just to illustrate the point. So that one's quite small. The size of it is, in terms of width, only a few inches wide. It is quite long, but I used it here to try to illustrate some ceiling leakage. So let's take a look at the results of this. And yeah, it's half an inch. It's 6 inches, but it's 150 feet long, but it's 6 inches. So let's take a look at the output. Now here I ran a study with I did a crack failure analysis. In CoolSim, you can run up to 4 variations at once. So I ran 4 variations on this. I'm supplying at 70 degrees Fahrenheit. It's an N+1 design, so I have enough air. I turned off one of the cooling units. The reason I did this is I wanted to show you again the effect of not being able to modulate the incoming air. So take a look at this. This is problematic right here. You can see I'm falling out of tolerance over on this side of the room, even though this is a hot aisle design. The reason for that is that that air handler over there is off. So if I take Pathlines here from cooling units, you will see that that particular unit is turned off. And the result is sometimes these get a little sticky, particularly when I'm doing presentations. So as I mentioned, this stuff won't always work. Here it comes. So here is the Pathlines coming. This is cold air. It's coming through that wall, same as before. We're very close here. The distance between this leading edge and this device, this air handler device, is too close in this design. And so it's causing very, very high velocity path lines or velocities down these aisles. Look, this one's running at 1,000, 1,500 feet per minute as it comes tearing down that aisle. There's also a bounce in it. It bounces off. You can see over here. Let me flip this around, see if I can. I'm using keystrokes here. Yeah, let's use that one. You can see the air coming through here and bouncing. Let me turn off a few elements here so that you can see a little better. Turn off blocks. There it is. So there's a screen that creates some pressure that tries to unify that flow a little bit. So that's a mechanism for breaking down the velocity and unifying the flow. But it does cause some swirling over here of the air, and the air bounces up and down the aisle. You can see it there. And because this one's off, the screen isn't quite sufficient in terms of its ability to make that flow uniform. If we look at it from the top, and you can see this one's not blowing at all. This row is starving for air, and that's how we're getting our problem. If we look at it from a pressure point of view, same thing that I showed you before, just more of it. In other words, the pressure is not always positive from the hot aisle from the cold aisle to the hot aisle. You want a positive gradient from the cold to the hot. If we take a look at some of the pressure here, y equals 7 is a pretty good representation. Yeah, I don't have that range tight enough to see it there, but we can see it in the thermal map. I'd have to tighten up the color range on that to be able to show you the gradient. I didn't get a chance to do that. But if we take a look at temperature, we can see it there too. Temperature, y equals 6. Yep, there it goes. So let's go to full screen. Let's take a look at the Y gradient, and let's turn off perspective so that, and you can see here that you want a positive gradient. You want, well, here we're looking at temperature. So you want the aisles to be hot aisles hot, cold aisles cold. This one's got problems. It's leaking around this section. So problems in the thermal and problems in pressure, same issue. Now we can take, let me put that one down. I'm going to go to one more design here that I have. I want to show you. This is another common slab design, and I'm trying to be sensitive to time here. I would like to open this up for discussion if we can, and I'm running out of time. I figured I would. I have too many models and not enough time. So you can begin to ask questions if you like, and I'll try to answer them. You can either do that. Okay, so here's some questions coming in. What is the horizontal line that separates north and south plan? What is the impact of underfloor obstructions? Sure, underfloor obstructions are always an issue, Mitch. Yeah, there's a target of percentage of obstruction. Generally speaking, on the underfloor, if the obstruction is not greater than 30% of the cross-sectional area in height, then it tends to not be as much of a problem. So you don't want it to be more than 30%, generally speaking, of height. And when the customer does not specify the airflow demand from the racks, what is the software standard? Is a kind of rule of thumb that correlates? Yes, Diego, I mentioned about 100 CFM per kW. That does vary depending upon the age of the servers. In the old days, we used to make that 150 to 156 is where we had it. But it's been coming down because the servers are becoming more efficient. And so they're able to in terms of their heat dissipation. So their appetite is a little lower for CFM per kW. So now it's down around 100 and seems to be dropping. In other words, they're getting better and better at that. Well, let me show you this design. This is one that I saw. I put this together after looking at some different designs that I've seen. Again, outside air, These are probably Kyotos or something. So these are fan coils sitting on the wall. And just the configuration of this alone, just looking at this, I can tell you where the issues are going to be based on experience. These units are sitting far enough away. I mean, look at the distance that you have to put in place in order to keep the velocity from bothering these racks. And so this one is far enough away. This distance needs to be, generally speaking, well, it depends again. The problems with rules of thumb is it all depends. So I would say at least 8 feet or more. The other problem here is n+1. This is going to cause some asymmetry. If one of these units is off, it's going to cause asymmetry in the room. If there's leakage in these racks, particularly in these racks here, the air is not going to get over onto this side because the air is going to escape into the contained area. So, and in this design, the pressure gradient is going to be towards the center if there's any air left. Let's take a look at some of the output for this. First, let's look again at our favorite recommended temperatures. Yeah, see what's happening here is there's no air left for the middle of the room. By the time the air leaks through the contained area into the ceiling, there's no air left to satisfy the needs of the racks in those sections. Furthermore, those sections are the narrow sections. That's where the high velocity air is going through. So the pressure gradient is not positive all the way down those aisles, and we can likely see it in temperature. Temperature is the easiest place to see it. Let's take a look at the top of the rack, see if we can see it there. So here's a slice at 7 feet. Let's go in and take a look. Y, N. So I use the Y key and the N key to line this up. And you can see that I've got temperature building up here and pushing through. Yeah, this rack I'm a little above here, and in this model they did not model the racks uniquely with leakage in the rails. They're using just leakage in the baffle itself, which is a first order approximation. It's not bad. Let's take a look at pressure here, see if there's a pressure gradient that we can see. Oftentimes in pressure we have to adjust it because the air handlers are creating so much pressure it tends to make the display L1. By the way these things work is that it'll take the min and the max of the flow field and spread color out across it. So if you've got some very high pressure supplies, then you won't see much gradient because they tend to dominate the color scale. But here we're looking at, again, fairly even pressure. There should be a gradient here. Between here and here, there should be a gradient, and I'm not seeing much of a gradient due to leakage. So even though we're dumping more into the room than is needed, we're not seeing the positive pressure gradient that we'd like to see. Now, in contrast, I have this one, which is the same exact design. Let me drag it over. But I put a floor plenum underneath it. And in this case, my floor plenum's not that deep. And the other thing I did here, which I simply took those air handlers and stuck them under the floor, which is not quite right because the cross-sectional area here is fairly small, which means the velocities are going to be high. If you were to do this design, it would be best to flip these 90 degrees and drive the air straight down, let it bounce off the floor, let some of that momentum decline, so that you have higher static pressure. So same design, however. Now what's interesting here is let's go take a look at that same plot. And I've done no magic here. There's nothing unique that I've done to this design other than to put the floor in place. In fact, the percent area open on these tiles is all the same. And I think I've got it set at about 30%. But look at the performance. It's better. Where the other one was showing a lot more red, this one is not bad, and furthermore, this is manageable. For one thing, with falling out of range on the edge like that suggests that probably I don't have much in the terms of servers there anyway, and I could manage that through perforated tiles. There are tiles out there that are what we call performance tiles. They have fins underneath them that allow you to capture some of this air that's traveling by at high velocity. That's what's going on there. It's the air is going by at high velocity, and it's bending up, and so it's not getting to that edge. You can manage that with performance tiles. On this back edge, it's likely we have some velocity there too that's causing those to do the same thing. But when I see a design like this, I say, well, that's manageable. One of the things you can do is be careful of those racks. Don't put 8kW there. Save it for the center. If you are going to put 8kW there, then you have the opportunity to add another tile in the center, make the tile higher, percent area open, use performance tiles. So this is manageable. Plus, in the N+1 case, it's just much better. It performs better because I don't get this tremendous asymmetry with respect to the flow. In the earlier design, I had a terrible asymmetry in that flow. Let me just go back to that one again. This is the design with, and you'll see over here, I'm having some trouble because the air doesn't get over there. So let's take a look at some pathlines here from the cooling units. And I see them coming up on the top of the hour, but look, most of that air is going into the center here, right where those air handlers are. And by the time it gets over here, there's not a whole lot left. So the servers over here aren't getting, and this is in the case where they're all on. Now, if this were a supply plane I'm staring at, that would all unify and I could use the tiles. It's essentially a manifold. The raised floor becomes a manifold from which you can modulate the amount of air coming out of it. In the non-raised floor, you cannot. And what you're at risk of is leakage. As these start to leak, you lose control and the quantity of your cool air, and there's not much you can do about it. So the risk operationally for non-raised floor data centers is that whoever does the installation of the servers and the racks doesn't manage the leakage correctly. They don't watch the rack rails around the perimeter of the rack. A big area of concern is under the rack, making sure it's sealed under the rack, make sure the perimeter of the rack is sealed against the contained area, and then within the rack, making sure the rack rails are sealed on top and on bottom and on sides, and all blanking panels are in place. In other words, the risk is higher of operational problems in these designs because there's no way to compensate, no way to modulate the supply air. So I got through them. I got through most of what I wanted to do. It's top of the hour. Summary slide down here at the bottom. And let's go for questions. On the opposite side of the CRACs, if I install perforated doors on the racks and try to reduce the pressure, yeah, do you think you can improve the temperature of the racks? Yes, Diego, there's many things you can do to modulate this from the operational point of view, but it's an operational issue. You have to be there. In other words, someone has to do that, and the people who are operating the data center need to be taught. They need to be taught important issues like management of that air. And one of the things I'm a little bit concerned about here is that the elimination of the raised floor data center as a design of choice is a capital expenditure issue. Fundamentally, the cost of putting the raised floor design in place can be avoided using some of these fan wall designs or some of these flood the room air designs, slab designs. However, they are not thinking about the operational cost. If I have leakage and the room is not managed well from an airflow point of view, then I have to either run the temperature lower or the fans harder to make up for that. So where you can drive the amount of supply air more closely to that that's demanded by the rack in the raised floor design, you don't have that freedom in the non-raised floor design because you can't modulate the amount of air coming into the room. It's all been done by the big fan wall. So it becomes problematic. Raised floor, Sharon, hi Sharon. Raised floor designs must be chosen more carefully. Modern day servers are now much heavier. Yeah, that's true. So you have static loads, static pressures, a bit more intense. Yeah, perforation of the tiles, you are right. They have to be strong enough to be able to handle the load. That's true. So you need to worry about weight and static load and just heavy load for sure. Bill's asking, does IT equipment in the rack also have its own local fans? It certainly does. For regulating airflow, it certainly does. They have their own control system. And to be honest, none of us know exactly what those control systems are doing. The numbers I gave you of 100 CFM per kW is a rule of thumb that may not be valid. I was an electronics packaging engineer as a young person. One of the first things I did as a mechanical engineer, and we oversupplied, right? Why not? Why not oversupply if you're in doubt? So the risk that the fans are pulling air in at more than they really need is going to be problematic as well, because then you'll need more supply air. And modeling this is difficult because the manufacturers all have their own thermal control systems inside those servers, and they're not willing to share with us what those look like. All we know is that from a heat transfer equation point of view, we need approximately 100 CFM per kW as a minimum amount, but it may vary depending on the kind of service you need. Furthermore, in that non-raised design, the high-speed velocity air that's passing in front of those racks on the way down the aisle will cause a pressure differential that will make those servers work much harder because the air going by them is perpendicular to their intended direction. So that will cause the servers, what we call, to scream. The servers will scream because they're trying to cool and they're having difficulty operating due to their high differential pressure. So beware of this when you're designing these systems. Be sure to point out leakage. Be sure to model leakage and understand, particularly in the N+1 case when one of those air handlers is off, how the system's going to perform. Be careful of having rack rows too close to fan walls or other high-speed air devices that are moving in a horizontal direction or perpendicular to the server itself. And use CFD to try out different scenarios. The CFD is a great way to say, you know, what I did here is raised floor versus non-raised floor. Fairly easy to take a non-raised floor design, throw a floor underneath it, mock up the model and run it and take a look at the overall performance of it. Again, I think many of these decisions about slab designs or non-raised designs are a capital expenditure discussion. CapEx is lower. But what I'm seeing is the operating costs are going to be higher, and the operating costs last longer. The capital cost is incurred once. The operating cost is incurred every single day. And with the cost of energy going the way it's going, it's important to consider this early on instead of, you know, dealing with the high operational cost later. So Murray had a question: if the IT provider has the ability to override the control on their internal fans, is it a value input for modeling? It can be. It can be, because we're making assumptions about the amount of air required by the server. So if there's a way to control that, and of course there is, you can control in some cases, on some machines, you can control the amount of air that's going through the device. Unfortunately, many people use that to turn them on full. They just turn them on full speed and override the thermal management system so they have no hotspots. But there's only a certain amount of air in the room, and if you pull too much in places you don't need it, it's going to sacrifice it for the rest of the room. So I'd like to thank you for this. If you have more feedback about this kind of topic, if you want to study it more, if you want me to do more models, I'll try to do these. I'm trying to do these once every month if I can. It takes quite a bit of time to run all these models and get this prepared. I'm also doing it as a multimedia system or session so that I can share some of this output with you and show it to you. I thank you for your patience with respect to getting this all done. And if there's anything we can do to help you, please let us know. Thanks. Have a good day.